Hey, it's Jim, and this is FRM Part 1, Book 2, Quantitative Analysis, and the reading on Machine Learning and Prediction, Part A. We'll go ahead and take a look at the first 3 learning objectives in Part A. Then we'll come back in Part B and pick up the last 5 learning objectives. Let me just quickly remind you that in that previous reading, which had a Part A and a Part B as well, we were focused on understanding the limitations of classical regression analysis and under what conditions we need to try to find some other kind of a model. And that's where machine learning comes in, because with machine learning, we're able to handle large data sets without those restrictive assumptions in the classical econometrics models. Let me also remind you that we spent a good bit of time talking about overfitting and underfitting and the problems associated with simplification and complexification. And so we're going to just continue along in at least the first half of this reading. And our focus is going to be on what are some other things that we can do that weren't mentioned back in that previous reading. And so there are the first 3 learning objectives of this reading. We'll go ahead and talk about linear regressions, and then we'll have some good time talking about a logit model or a logistic regression, which relies on encoded categorical variables. And then we'll talk about Ridge and LASSO at the end of this slide deck. So let's go ahead and look at that first simple one. I'm guessing I don't need to re-explain the role of linear regression. The issue then becomes, what happens if we have a model in which, and let me go back to Part A and Part B of that previous reading. Remember, I had the scenario where a customer walks into our financial institution and is the owner of a business and wants to borrow a couple $100,000 or a couple million for a positive net present value project. Wouldn't it be awesome if we could just immediately determine whether or not that client is going to be able to repay the loan? Well, linear regression fails in many instances if we're trying to predict some type of a probability that must be between 0 and 100%. I mean, that makes perfect sense. So the logistic regression allows us to have some kind of a variable in which the only outcome is a 0 or a 1, repay or not repay that loan, default or not default. So we use this logistic regression model because sometimes when we use linear regression, we might get an answer that sounds like, oh, this customer has a 116% chance of repaying the loan, or a minus 17% chance of repaying the loan. And of course, that doesn't make any sense at all. My son always points out whenever an athlete on the field is saying, oh, I gave 110% today, my son always says, boy, I wonder how that happened. So what we're going to do is we're going to continue talking about extensions of linear regression. Now, you might remember we talked about regularization just a little bit back in Part B, and I warned you that we were going to talk more at length about that here in this reading. So that's going to be our first kind of a conversation, and there's the logit model or logistic regression. Notice down on the bottom right green there, probabilities predicted are within a valid range between 0% and 100%. And this allows for this binary classification. And it could be something as simple as default or no default, or something as simple as the S&P 500 index is X at the beginning of the year. Is it going to be above or below during the course of that year by the end? Now, regularization is this process by which we take a look at our complexified model and we say something like, you know what, this is too complex. How can we shrink it? How can we regularize it? How can we reduce the complexity of the model? So that's pretty much the focus, at least in these first 3 learning objectives here in this reading. So let me show you just a quick picture of what you know from going way back in your life. Linear regression. This is the ordinary least squares model. And if you look at the blue dots of data points, what ordinary least squares does is it just takes a ruler out and it measures the distance between each one of those points and some hypothetical line, and it minimizes the distance between those points, and you come up with a measure of the intercept and you come up with a measure of the slope. And that's what ordinary least squares does. It throws a line in there because it assumes, of course, that the relationship between the independent variable and the dependent variable is linear. But remember how I emphasized this back in part A and part B of that previous reading. We're not really calling these things dependent and independent variables. We're calling them features because there are so many of them. Now here's this expression for the multiple linear regression. There's alpha for the intercept. There's beta 1 and 2 and 5 and 10 all the way out to 100. That's the slope measure of the sensitivity. And then x1 and 2, those are our independent variables. And so what are we trying to do here? We're trying to do this residual sum of the squared, and we call that just the RSS. That's the difference between the actual value and the predicted value. And so what do we want? We really want to say something like, hey, our model is really, really good. It captures all of the dynamic relationships that are out there, and it is able to predict with 100% accuracy the next variable in sample or out of sample, whatever the terms that we used back in our classical econometric model. Well, of course, we're never going to be able to accurately predict those values. But what we find is that when we get into machine learning, that those sum of the square differences using ordinary least squares, they just become massive or they become zero. In either case, then it's not really important to us, and it's not really useful. All right, so this easy to understand and interpret. Those are the advantages. Linear relationship, we talked about that before. Normal distribution, constant variance. Limitations, look at this. Prone to overfitting. Now that's something that most of the time you don't hear in your regular old statistics lecture. No multicollinearity. And then look at the fifth limitation. This is what I was saying before. 114% chance of doing something. That just doesn't make any sense. So what the logistic regression does is it turns, let me go back here real quick. It turns this line, remember ordinary least squares, we're forcing this into a line. What it does is it converts it into what's known as a sigmoid, which I guess stands for S, right? There's a little S curve. And notice on the vertical axis, we start at the origin of 0 and we go all the way up to 1. So the logistic regression forces the output to be something between 0 and 1 so that we can make probability predictions. And so this sounds like a pretty good exam question under which, if I were doing this at the super simple undergraduate level, I would say something like this. I would give my students this graph here with a line, and I would give them this little S curve and say, explain the difference between the two. And the answer, of course, would be, one is ordinary least squares and one is a logistic regression. And so to understand this logistic regression, we need to find that little e to the x button on our calculator. Remember, e is the base of the natural logarithm, and we know it is a constant. We know it is 2.71, however many digits it goes out to. What does it go out to, a million or a trillion? So we know it is a constant. It's the base of the natural logarithm. But what we want to do is we want to figure out what that means for us in finance. And the easiest explanation that I can give you is the following simple time value of money example. You have $100 today. The interest rate is 10%. How much are you going to have at the end of that first year? Well, we don't need a financial calculator to say 110. And that's assuming that interest is compounded annually. But we know that interest can be compounded over any time period. I mean, any bank could say, hey, I'll pay interest every 42 days. I mean, I'm Jim's bank. I could say I'll pay interest every century. I mean, that doesn't make any sense because most banks will pay interest more than one time a year rather than less than one time a year. But we can do semi-annual, quarterly, monthly, daily, right? All those different things. And the most frequent form of compounding is continuous compounding. And so we need this base of the natural logarithm to be able to compute that future value. And that, by the way, is the maximum future value of that 100. And so if you put this in your calculator, e to the x, and x in this case is going to be n, which is 1, times the decimal form of the interest rate, which is 10%. So if you do that and hit your e to the x button, you get some number like 1.105 something. And so the maximum future value is going to be 110 and 52 cents, or I'm doing a little bit of rounding there. And so we're going to use this e raised to the x, which is essentially a continuous compounding of the growth rate of our $100, or whatever that number be. It could be revenues. In the medical profession, it could be, I'm making this up, the number of cells inside of a tumor, or in engineering, it could be tensile strength. I don't know what I'm talking about with a bridge. All I know is that when you drive over the Chesapeake Bay Bridge in Maryland, you can feel the swaying back and forth, and the engineers tell us that's a good thing. So all that stuff is super useful. We can convert that little e to the x to some expression that fits into our logistic regression model. So what we're going to do is we're going to convert that. And look at the very bottom. There's a probability. We're just going to take that e to the x in the numerator, divide it by 1 plus the e to the x. Now, in our case, the e to the x is the entire multiple regression equation. And so we're imposing this probability inside of our linear regression model just by assuming the use of that e to the x. Now, the way that this is done from a technical standpoint is through something called the maximum likelihood estimator. So we get rid of the ordinary least squares model. We use this maximum likelihood estimation, and it looks an awful lot like that in the gray box down at the bottom, where that maximum likelihood estimation is a function of the y. Now, y is our entire regression equation, and so that's what's known as the cost function. Now, that thing there is a little bit too daunting and cumbersome, and so what we do is we take the log of both sides, and that allows us to take this, maximize the log likelihood function, and this then becomes our logistic regression model. So look at the bottom box down there. There's the 0 and the 1. So these are thresholds. So because of all of this transformation using, the basic little e to the x button on our calculator, we force the data into output that says something like, 12% probability or 47% probability. We're never going to get to the 114% probability. Now, what we can do is we can have some prediction, or we can have some classification. Maybe stock returns are either positive or negative. So that's a kind of a yes or a no. Here's just a quick example here up in the blue. Whether a customer will default based on two variables, credit score and debt to income ratio. 500 customers, and so there's our probability of default. This is the output of the logistic regression model, which is a function of all that. Let me just go back here real quick just to show you. It's a function of this maximum likelihood with all this stuff in here. When I was in graduate school, we did this just a little bit. I never touched this on my dissertation. But we were just given a whole bunch of data and we just threw it into a computer and it produced this output. So what can we do is we can substitute, well, let's suppose, go down to the bottom left. There's a credit score of 650 and a debt to income ratio of 0.6. So if we just take those numbers and throw them into the numerator and the denominator, well, the math comes out to about 12%. So what can we conclude? 12% probability that this customer will default on the loan. Now, what we can do is we can take that 12% and say, what do we want to do with it? Do we want to say, how does that help us with a decision? So what we do is we can convert it into some binary prediction. So what we've done in the bottom right here is just say, hey, let's just take an arbitrary 50%. Anytime that probability is less than 50%, we'll just classify this as no default. So you see how back here we're predicting and we can classify. So that explains that learning objective. Now, of course, this categorical data doesn't take on a numerical label. So these could be names, they could be attributes, they could be some kind of some label. We can do mapping, we can do encoding, we can do non-ordinal categorization. We can create dummy variables, which are just 0 or 1. We can say that these are marked of whether they fit into one particular class or one particular feature or one particular arena. Let me give you a silly example. How about this one? Tom Brady is retired. Tom Brady is not retired. Maybe you throw all that data in there, at least in 2022 and 2023, the model probably explodes. So let's go ahead and take a look at an example here. Notice that we have 0 and 1s, and we don't really need to be limited to just 0 and 1s. We could put there 1, 0, 1, 2, and 3 and 4. We could do all that for, well, in this example, we could have a candidate's grades are poor, good, or excellent. But in most of my experience, in fact, I'm not sure I ever worked with more than 0 or 1s. What you fall into is what you see up here. So you got 0 and 1s, and these are just, sectors, and they could be, almost anything. They could be performance. They could be whether or not you think that the industry has good leadership in its leading firm's board of directors. It could be whether free cash flow is positive or negative. I mean, it could be almost anything here. And so what happens is that if we collect massive amounts of data, we might not be able to fall into remember we called this, like the ordinary least squares was, the least squares, right? The maximum likelihood estimator. Well, with the dummy variables, neither one of those models may perfectly, I chose that word incorrectly. They might not nearly perfectly or reasonably be able to give us some kind of a prediction. So what we do is we do this process of regularization, and we can do this in two ways. We can do a ridge regression, or we can do a LASSO approach. And so think about this massive amount of data that we have. Think about all of the issues that we talked about in that previous reading about machine learning, supervised and unsupervised, and reinforced learning. And we've got this huge data set, but it's too complex. What we want to do is we want to reduce it. We want to simplify it. Now, of course, we don't want to oversimplify. Remember back in part A and part B, we showed you a graph, right? Marginal costs and marginal benefits, the difference between the bias and variance. And that was a decision that we made based on the costs and benefits at the marginal point. And so what we're trying to do now is we're saying, look, we got too much stuff. We need to shrink it. So what are some two possible shrinkage models? And of course, as a good fan of Seinfeld, I can't help but state the relationship between ridge regression and LASSO and shrinkage on that really super funny Seinfeld episode. Now, notice what we're doing here in this regularization. We're saying something like, look, we have all this data. What will tend to happen is our coefficients of our features might be too high. And if they're too high, they might be unwieldy and they might not be prone to prediction. Remember, I said this just a few moments ago, that the predictions might be way off. They may be way too high or too low. So what these two methods do is they add a penalty term. So remember our conversation on that reinforcement learning where we had an agent who was inside of a box making decisions. And in that case, the agent was rewarded for successful decisions and penalized for unsuccessful decisions. Well, now in regularization, what we're doing is we're just penalizing because we want to shrink a too complex model down into one that is, well, not too simple, right? Another Seinfeld reference here. George says he wants to give the internship to somebody who's right in the meat of the curve, not showing off, not falling behind. So remember, our goal is to come up with an optimal model. We had that on the graph back in that last reading. So it reduces the impact of correlated variables. Remember, if we have multi-collinear, that just throws that whole regular old classical econometrics model out the window. But what happens here with machine learning under regularization is that the algorithm goes and finds patterns inside of the data. So instead of needing 4 features, let's say, it finds patterns in there and says, you know what, we don't need these 2. Maybe we don't need these 3. So we're left with just 1 or 2. And look at the bottom one. I love this thing. Rely less on the influence of any single variable. What we're trying to find are themes inside of these features. Now, remember, we did talk about normalization and standardization. Let me just quickly remind you, standardization, we kind of divide by the standard deviation. Normalization, we divide by the difference between the max and the min. And so that improves the generalization. And how do we do this? Well, what we're going to do, and once we normalize and standardize, then we're going to regularize. And we're going to do it through Ridge and LASSO. So let's go ahead and talk about Ridge regression. I'm going to go ahead and give you a very likely answer on the exam. Forget about all that stuff here. We'll do that here in just a second. But look all the way out to the far right. There is a slope coefficient, beta hat sub I, and it is squared. This is the ridge regression, and it is a penalty. So I want you to think of ridge as the squared penalty. Notice there's a term alpha there. This is just, it's a constant, it's a parameter. Actually, it's known as a hyper parameter, and it's a value that is set. And we have an example here in just a few minutes, and you'll see the difference between and how sensitive these models are to the selection of that lambda. And so all we're going to do, let's go back up to the equation. This is a loss function. It's called a loss function in ridge regression. And notice what we're doing. There's the sum, and there's the y hat. So that's our model. And then we're just throwing variables into our estimated alpha and beta coefficients. And we're taking the difference between, what the model predicts and what's actually out there, right? This is the residual sum of squares that we were talking about earlier on. And then we're adding that penalty term. Notice that the second term is known as the shrinkage term. Those of you who watch Seinfeld have to get a chuckle out of this. And maybe that chuckle that occurs to you while you're taking the exam will lessen your anxiety and put you on a path to great things, great exam answers. All right, so here's just a little summary page, a summary slide of what we talked about before. There are the model parameters, alpha and beta, and there is the hyperparameter of alpha. Now, let's move on to the least absolute shrinkage and selection operator. I'm just going to throw you all the way over to the far right and take a look. There's the beta hat sub I. Let me go back here just quickly. There's the beta hat sub I, but in ridge, it's squared. And in LASSO, we just take the absolute value. So, as you can imagine, then this penalty is very different from the ridge regression penalty, but it's still a penalty. I regularly asked you guys to get your phones out and take a picture of a slide. This is a beautiful one. So let's go through this. Go ahead and take that picture. The reading does emphasize L2 regularization and L1 regularization. I can't imagine that you would get that on the exam. Just remember the 2 is for the squared, then you'll remember ridge regression. But what I like about it is that, what is that? 1, 2, 3, 4. So we're adding a penalty term under ridge that shrinks the parameters towards 0, but not all the way to 0. And this is surely useful when there's lots and lots of multicollinearity. LASSO, on the other hand, go ahead and skip all the way down. It sets some of the less important parameters to exactly 0. So you see the difference. This is the very likely exam question that's going to show up. Just define and describe the difference between the penalty terms, and you will have this on your phone, and you will read it 27 times before the exam, and you'll be able to do that. So that seems pretty good and pretty straightforward. Now, what happens if you say something like, you know what? In lots of quantitative analysis, we go ahead and try to take the best of both models. Well, that's what this elastic net is. It just combines the L1 and L2 regularization. So skip all the way out to the far right. We have an alpha 1 and a lambda 1 and a lambda 2 with the beta hat squared and the absolute value of the beta hat. So the elastic net, of course, is a combination penalty model. Now, why do we use this? It'll decrease the magnitude of some of those parameters. It'll eliminate even more clearly some of those unimportant parameters, and it hopefully will improve the model's performance. What did I say earlier? Not showing off, not falling behind. We're trying to get to that optimal model. So let's take a look at a quick example. This is a comparison of ridge and LASSO. So look across the top gray box. We've chosen alphas of 0.1 and 0.5 for ridge, 0.01 and 0.1 for LASSO. And here we have the intercept, and we've got 5 of those features down there. So look, under the ordinary least squares model, look at those slope coefficients, a 20, a 50, a 30, a 10, and a 5. And so, man, are we really able to accurately interpret what those things mean with massive amounts of data? And the answer is, well, let's go ahead and see what shrinkage does. Well, what does the shrinkage do? With the ridge regression with an alpha of 0.1, and that's the second time I've said that. A lambda of 0.1 and a lambda of 0.5, notice that we are shrinking. And as we increase lambda, well, we go from, the intercept 245 to 233, but now notice there's a dramatic shrinkage for those features. 623 to 19, 999 to 232. Everybody see that? So with ridge, what is it? What did we say in that earlier slide? Those parameters then get closer to 0, but they approach 0, but they're not going to be 0. Now under LASSO, what's going to happen? Look, there's a bunch of zeros over there, so we can conclude that, feature 3 and 4, let's throw those out. Those are not important, right? Maybe if we set the lambda all the way up to 0.1, we're left with only one important feature. So do you see how this is a super cool example of shrinkage to try to manage these huge data sets? Let me go back to my very first example in part A of that previous reading where we were comparing LeBron and Kareem, and we're trying to say something like, tell me how we give the machine an algorithm. Tell me how each one of these super talented men scored 38,000 points in their career. And remember I said we had all this data, like number of steps taken on a court, distance with the made shots, number of foul shots. But then remember I said something like, how many times does LeBron and Kareem go this way and make a V cut that way? Well, in the ordinary least squares model, we might get an intercept term that's influenced by that independent variable, and we might have a slope coefficient that might be statistically significant. And so we scratch our heads and say, does it really matter if LeBron cuts at a V angle that's 90 degrees or 72 degrees or whatever it is? But with LASSO over here, it's going to identify that we really don't care about the cutting angles on the court for these two athletes. What we care about are things like shot selection and number of foul shots made, and for LeBron, number of threes made, et cetera, et cetera. So this is really a cool thing. And I'm guessing that on the exam, you would get a table similar to this, and the question might be, tell me what is the positive conclusions. And of course, you would do this in multiple choice form. So here's a kind of summary page. You might want to take a picture of this as well. But this is pretty much everything that I have talked about over the last, what has been 30 minutes or so. So there's the learning objectives. So we'll come back for part B. What I want you to do right now is I want you to go to the reading and just quickly go over the first, I think there are 15 total questions at the end of the reading. And there may be 4 or 5, maybe 6 that apply to these first learning objectives. Just go through them quickly and see if you can't do that in 10 minutes to give you a sense, because after we're done part B, I'm going to have you go and spend 30 minutes on those questions. And hopefully our recordings give you a really good leg up in solving those problems. So, hey, thanks for watching. I had fun today. Good luck studying, and I'll see you in part B shortly.